Why is fitting embedded C code into tiny memory so hard? Imagine trying to fit a large puzzle into a tiny box. That's exactly what developers face when working with embedded C code on microcontrollers with very limited memory. These microcontrollers often have only a few kilobytes or even just bytes of RAM and flash memory. This tiny space must hold everything: the code, the data, the stack, and the heap. Every byte saved counts because running out of memory can cause the system to crash or behave unpredictably. Embedded C programs are designed to be efficient, but managing memory is still tricky. The code itself takes up space in flash memory, while variables, buffers, and stacks use RAM. If you use large data structures or many pointers, you quickly eat up available memory. For example, storing many pointers can be costly because each pointer might take 2 or 4 bytes. This makes it essential to write compact code and avoid unnecessary variables. The stack is another challenge. It holds local variables and keeps track of function calls. If functions call each other deeply or use recursion, the stack can overflow. Since the stack size is often small, developers must limit function nesting and avoid recursion altogether. The heap, used for dynamic memory allocation, is usually avoided because fragmentation and unpredictable allocation times can cause system instability. Real-time performance adds to the difficulty. Embedded systems often need to respond quickly and predictably. Using complex algorithms or dynamic memory can slow things down or cause delays. Hardware-specific memory architectures also complicate things. Different microcontrollers have separate code and data memory spaces, or special registers, which means developers need to understand these details to optimize memory use. Embedded C is a subset of standard C, tailored for hardware. It often lacks advanced features like automatic garbage collection or flexible memory management. Developers relying on manual techniques such as using unions to share memory, static allocation instead of dynamic, and passing large structures by pointer to save space. Balancing features and size is a constant trade-off. Adding more functions or features increases code size, but removing them might limit capabilities. Inline functions can reduce call overhead but increase code size. Optimizing for speed might requiring more memory, while conserving memory might slow down the system. To address these issues, developers examine the microcontroller's datasheet and memory map carefully. They minimize pointer usage, prefer static over dynamic memory, and use unions to overlap variables that are not used at the same time. Reducing function call depth and avoiding recursion helps keep the stack small. Passing large data structures by pointer instead of by value saves memory. Using compiler optimization flags can shrink code size, and profiling during development helps find and eliminate waste. In electrical engineering, these constraints mean designing software that fits within the physical and cost limits of hardware. It's about making sure the device runs reliably and responds quickly, even with tiny amounts of memory. The challenge is in balancing the hardware limitations with the need for functional, real-time applications. That's why fitting embedded C code into tiny memory remains a tough but fascinating part of embedded systems development.